Good morning, good afternoon, good evening. Welcome everyone to the training series, Fundamentals of Machine Learning for Earth Science. Of the three-part series, this is part 2, Training Data and Land Cover Classification Example. Once again, I am your host. My name is Brock Blevins. I am Training Coordinator for NASA's Applied Remote Sensing Training Program. Let's discuss our training objectives for this series overall. We hope that by the end of this training, participants will be able to recognize the most common machine learning methods used for processing earth science data, describe their benefits and limitations, explain how to apply basic machine learning algorithms and techniques, use an analysis-appropriate training data set to evaluate conditions and solutions for a given case study, and complete basic procedures to interpret, refine, and evaluate the accuracy of machine learning analysis. Once again, a reminder of the prerequisites. If you don't already have a good handle of the fundamentals of remote sensing, we suggest you take a look at our session 1 that we have on demand, Fundamentals of Remote Sensing. Attendees will also need to access Google Drive and Google Colab. So in order to do this, you'll have to have an email ending in gmail.com. We will have this training recording available within 48 hours, so you can go through these procedures at your own pace. Here's the schedule for each of the 3 parts of this training, April 20th through May 4th. There'll be one homework associated with this series, and it'll be made available by May 4th. This will be a Google form submission, and it'll be very similar to the questions that you are asked to reflect upon at the end of each Google Colab session. So with that, I'm going to hand this over to Jordan, who will introduce us to part 2, Training Data and Land Cover Classification Example.
Okay, so this is part 2 of our Fundamentals of Machine Learning for Earth Science. Today, we're going to talk about some of the training data generation, how we can do exploratory data analysis of our data, and then a particular land cover classification example. The outline of session 2, we're going to first kind of explain how to download some of the training data. We're going to discuss some of the exploratory data analysis techniques. We're going to extract data from tabular data sets and also from raster data sets. And then we're going to have an exercise where we're going to be doing training and prediction of these tabular and raster data set formats. Lastly, we're going to do some metrics and model evaluation. We're going to discuss the concept of cross-validation and how you can improve some of your models, even when you have small data sets. At the end, we're going to have a post-session assignment we're going to discuss briefly, and then we're going to have the QA session. As always, the resources for this training are going to be on the GitHub repository that we shared across the sessions. The objectives of today, after participating in this training, the attendees will be able to, 1, use basic programming procedures to download, use, and process remote sensing data, use an analysis-appropriate training data set to evaluate the conditions and solutions for a given case study, and complete basic procedures to interpret, refine, and evaluate the accuracy of the results of machine learning analysis. So with that said, please, Jan, take over.
So in today's training, we will use some remote sensing data set collected by an instrument called Moderate Resolution Imaging Spectroradiometer, MODIS in short. And I will give a brief introduction about the instrument and the data and how to access some of those MODIS products. First of all, MODIS is a key instrument aboard both Terra and Aqua satellites. Both satellites are polar orbiting, flying at an altitude between 700 to 800 kilometers, and orbiting around the Earth about 100 meters, and producing a stripe of the observation of Earth's surface. And the satellite observation will cover the entire Earth's surface every 1 to 2 days. And data acquired by those instruments will further processed and generate different products, including atmosphere, ocean, land, and the cryosphere. These products will help scientists to better understand global dynamics and the process occurring on the land, in the ocean, and in the lower atmosphere. Our group have multiple applications with MODIS products, and one of them is to use MODIS land products to generate global water mask at a 250-meter resolution. Such water mask plays fundamental and critical role in processing remote sensing data. For example, scientists rely on collaboration algorithms to convert spectral signals collected by MODIS instrument and convert those signals into physical variables such as surface temperature. If we mistakenly apply land algorithm to water pixels, that will definitely introduce unnecessary errors. So our goal is to generate a high resolution water mask over global and have a higher accuracy of water pixel and land pixel distinguished. In these slides, we list a high-level workflow of the process we take, and we use machine learning. And basic workflow are split into 3 different components. During the data processing, we subset and extract surface reflectance from the MODIS land products and apply quality assurance to filter out missing data or bad data. And we constructing training data sets. With those training data sets, we build random forest, XGBoost, light GBM models, and train with both GPU and CPU. We also conduct a few hyperparameter tuning technique to get a better model. And the final outputs will be annual and daily water land map, and also 7 class water maps per year. On the right-hand side, you can see our product compared with other products generated with the traditional method are slightly different. We have a different label on water or land pixels. Back to MODIS data, all MODIS products are stored at the Distributed Active Archive Centers of NASA. We call it DACs, and different products were stored in different locations. Each link depends on what your specific task. You can identify the MODIS products through different DAC center, and each link will lead you to the introduction of data products and different method to download and or view those data products. NASA also provide a map web-based interface to access all DAC data. MODIS is one of those data products you can access through Earth data search. Here I showed one example. You can use Earth data search to filter instrument, like select MODIS. You can view the list of MODIS products show up in the second panel, and you can also preview certain MODIS data products on the map. The next slide actually I did a spatial and temporal filter of a surface reflectance, and a small preview map will show up on the eastern part of United States. As a part of NASA open science policy and the related goals, all DAC are migrating their collections to the Earth data cloud, and the different centers have a different schedule to proceed. And on left-hand side, I show one example to migrating atmosphere data collections to the Earth data cloud. And some of MODIS data is already available in AWS cloud S3 buckets, you can access with AWS credential and AWS softwares to retrieve the data is necessary for you. All right, now I'm heading to Caleb.
Now we will look at exploratory data analysis. In the first session, Jules showed us this wonderful diagram of the machine learning pipeline. Here we will focus on a subsection of this pipeline. Exploratory data analysis, or EDA, is a critical step in this pipeline. EDA is the process of understanding the data that you have collected or that you are going to use in your machine learning model. EDA can help identify missing values, outliers, correlations, and patterns in the data through cleaning, pre-processing, statistical analyses, and visualizations to get a high-quality data set. Data quality is a critical factor that can significantly impact machine learning model performance. Poor data quality can lead to inaccurate predictions, biased results, and poor model performance, emphasizing the importance of high-quality data pre-processing and cleaning. Therefore, it is essential to ensure that the data used to train a machine learning model is of high quality. We can do this with proper pre-processing and cleaning to remove the outliers, missing values, and inconsistencies in the data, as well as identifying things like correlations and patterns by visualizing the data. Ensuring the data quality is high is critical for building accurate and reliable machine learning models that can be used to make informed decisions. The main data types that most people would be working with in a machine learning data set, in a training data set, are numerical, categorical data, text data, or time series data. Numerical data includes continuous or discrete values, while categorical data includes discrete values that represent categories or groups. Text data includes unstructured data in the form of text or natural language. Time series data includes data points that are collected at regular intervals over time and can be used to forecast future values or identify trends and patterns in the data. Off to the right, we see a real-world example from our MODIS training dataset. We use pandas to describe the dataset variables, and we can see if there are any null values, as well as the numerical data type. All of these are a part of the numerical data format. They are continuous, except for the water variable, which is categorical of water or not water. After understanding the data types, the next step in EDA is to clean and pre-process the data. Missing values can pose a challenge for machine learning models, so it's important to understand the extent of missing or null data in the data set we're working with. This includes handling missing values, removing duplicates, and dealing with outliers. Missing values can be handled by imputing the mean or median value of the feature by using more complex imputation techniques. Removing duplicates and dealing with outliers can help improve the quality of the data, which in turn will affect the model performance. To the right, we describe some methods to detecting and handling null values in pandas. We can use isNull to detect null values in a pandas data frame that's in your machine learning data set. We can also handle those null values using methods like dropNA to drop rows of your data set that contain a null value. You can use fillNA to fill null values with a special value like mean or median. We'll see more of this in our exercise and on EDA. In exploratory data analysis, visualizing data distributions is a critical step in understanding the underlying patterns and characteristics of a machine learning data set. By exploring the distribution of the data, we can identify outliers, assess the data's normality, and determine if there are any relationships or correlations between the variables. There are several common methods for visualizing data distributions, including histograms, box plots, and density plots. Here we're looking at histograms. Histograms provide a visual representation of the distribution of a single variable. Box plots and density plots show the distribution of multiple variables. Histograms are a graphical representation of the distribution of a data set. It shows the frequency distribution of a single variable, with the x-axis representing the range of values and the y-axis representing the frequency or count of the observations in that range. Histograms can be used to identify the presence of outliers or unusual patterns in the data. To the right, we see a histogram that shows the spectral response for a single MODIS surface reflectance band grouped by class. Up top is the class of not water. Down low is the class of water. What we can tell from this is that there is a significant difference between the range of spectral responses for this band across the top class compared to the second class, which is water. This lets us know that there's a relationship between the spectral response of this band and the water, not water classes. In machine learning, outlier detection is the process of identifying and handling data points that deviate significantly from the rest of the data set. Outliers can be caused by measurement errors, data entry errors, or represent genuine extreme values in the data. In either case, outliers can have a significant impact on the accuracy of our machine learning models, and it's essential to identify and handle them correctly. Box plots are a powerful visualization tool for detecting outliers. They display the distribution of a data set by showing the median, quartiles, and outliers. Outliers in a box plot are points that are more than 1.5 times the interquartile range away from the nearest quartile. Box plots can be created for individual variables or multiple variables at once. By visually inspecting box plots, we can quickly identify the presence of outliers in our data. We can see an example of a box plot here to our right. The box plot on the left is a box plot of a surface reflectance band where the points are labeled land. The box plot on the right is where the points are labeled water. What we see here is that there are some outliers in the right box plot labeled water. It could be the case that some pixels in there should have been labeled land, or a distribution isn't normal enough. Outlier detection is an essential step in machine learning, and visualizing box plots and scatter plots is a powerful tool for identifying outliers in our data set. By detecting and handling outliers correctly, we can improve the accuracy and robustness of our machine learning models. In machine learning, understanding the relationships between variables is crucial for developing accurate and robust models. Investigating correlations between variables can help us identify which features are most relevant to the problem we are trying to solve and improve the performance of our models. One common approach to investigating correlations in machine learning data sets is by using a correlation coefficient heat map. The correlation coefficient is a statistical measure that quantifies the degree of linear relationship between two variables. It ranges from -1 to 1, where -1 indicates a perfect negative correlation, 0 indicates no correlation, and 1 indicates a perfect positive correlation. The sign of the coefficient indicates the direction of the relationship, with positive values indicating a positive correlation and negative values indicating a negative correlation. By using this correlation coefficient heat map, we can identify which variables are highly correlated with each other. Highly correlated variables can lead to multi-collinearity, which can cause issues in model interpretation and lead to unstable and unreliable model coefficients. Therefore, it is important to identify and handle highly correlated variables in the dataset before developing our machine learning models. A correlation coefficient heat map is a powerful tool for investigating correlations between variables in a machine learning dataset. By identifying highly correlated variables, we can improve the performance and interpretability of our models. However, it is important to remember that correlation does not imply causation, and other factors may be influencing the relationships between variables. Here we take a closer look at the correlation coefficient heat map of our MODIS training dataset. As expected, we can see that some bands that are closer together in wavelength have a strong relationship with each other. We can look at how each band affects the water classification. As expected from seeing our histogram of the distribution of values, we can see that a lower value from each of the bands trends towards a classification of water, although no band stands out by having a very strong negative correlation. In conclusion, EDA is a critical step in any machine learning project to understand the structure and properties of the machine learning dataset. Visualizations and analysis techniques such as data distributions, correlations, missing value handling, and outlier detections can provide valuable insights for feature selection, pre-processing, and model selection. With these EDA techniques and tools, machine learning models can be developed with a better understanding of the underlying data. Now that we've talked about exploratory data analysis, let's do some in practice. Here we're at the Arset ML Fundamentals GitHub, and we can access our next exercise. It is the Modus EDA one, and we can click on the link to open it in Google Collaboratory and run it there. Remember, you do have to have a Google account to access this. This is an introductory notebook to familiarize yourself with EDA techniques for machine learning. For this work, we will use data from the Modus instrument to test several data science techniques and machine learning algorithms. The intent of this notebook is threefold. First, an exploratory data analysis is conducted to visualize the optical data of the Modus instrument and the distribution of this tabular data set across water pixels. Next, this notebook briefly reviews the correlation of some of the spectral bands in the task of water classification. Finally, we introduce the topic of feature engineering and outlier detection that might be of use for other applications. This entire work is done using the Python programming language and based on a dataset uploading to Hugging Face. So here we're going to start running. Remember, we're going to get this warning. That's okay, we wrote this. So while the collaboratory environment has many of our packages like before, we still need to install some of our own. So we've installed the packages that we need. Now we're going to import some other packages that we'll use for performing the exploratory data analysis. We're going to define some general variables that kind of sets us up. And we're going to load in our data set. This is coming in from Hugging Face, a tool that you're able to share data sets and models. We load this into a Pandas data frame, and we can kind of examine a sample of it here. We see that we have our water classification, and we have our surface reflectance bands that come from the Modus instrument. We also have some calculated indices that are some indices that are calculated from the surface reflectance bands. In this section, we'll start to inspect and understand the nature of our data set. The simplest first step when we have a data set is to inspect the data types, columns, attributes, and the shape of our data set. Here, we see that all of our data are of type int64. We don't have any null values, and we have 800 of these values. And we have 10 columns variables. Pandas provides an excellent function to inspect the contents of our data frames in a more concise way. Note the number of observations per feature and the minimum and maximum values per Modus band. Unfortunately, the describe function does not provide any information for us to notice if there were any no data values in the dataset. For example, let's copy a row from the dataset and introduce a no data value in the water column, our label, and note how the describe function from Pandas does not change the overall statistics besides showing an item less in the count section. Here we do that. We put in the first as nan, and then we look at the describe and we see that there is no sort of indication that there is a null value. Thus, if we want to know if our data set contains any no data values, we need to perform one more step in order to understand which columns might have no data values. We can use the isNull function, which gives us the rows that show us where there's a null value. We see here, sure enough, that we have a nan value in our water column. There are many ways of handling no data values in machine learning. We'll not dive too deep into the details of it, but as a general idea, we can remove rows with no data values. And if we know no data values belong to a specific group, we might be able to convert it to the appropriate value. For example, our digital surface model returns no data values only on water bodies, which could be useful to apply here for additional data points. Once we have dealt with our no data values, we can go ahead and visualize some of the data to understand its structure and find any patterns. Here we're taking a sample of the overall data set, 10% of it, to speed up some of the visualizations that we're going to perform. This will still give us a general idea of what the overall data set is doing, but is useful to do if your data set is too large and it might be too computationally expensive to perform some of the tasks here in our exploratory data analysis. We see another sample of the data set. And here we're going to do a correlation plot with water points as the orange. This is a lot to take in, but what we can read from this is the X and Y axes are our bands, and those are the correlations between those bands. So we can see down here, we see the correlation between NDWI, the normalized differentiable water index 2, and the surface reflectance band 1. The orange points are the points labeled water, while the blue points are the points labeled land. We can see there are some sort of relationships, but it's a little messy to tell. We can get a little more idea from some other points, such as surface reflectance band 5 and surface reflectance band 2. We can see that there's a little better grouping of the land pixels against the water pixels that are down here. This is useful in telling the correlation relationships between different variables, in addition to being able to separate those correlation relationships between land and water values. Another good practice is to understand the distribution of values for each column feature. This will show you where most of your data lives for each feature in the data set, including the distribution of training labels. Here we have a pretty perfect split between land and water values, so we would expect to see almost the same number of land pixels and water pixels in our data set. Now we have the distribution of the total data set of each of the bands. We see it doesn't look like a totally normal distribution where you have tails on both ends. This is mostly because we have the water distribution is different from the land distribution, and combined it makes it look a little strange. We can see here that we have two humps, and we can kind of identify that this may be the water distribution off to the left, and off to the right we have the land distribution. Now, how can we do a more statistical approach to correlation using, we can use the pandas core function. This will give us the previously talked about correlation coefficient heat map that we had seen earlier. This tells us between -1 and 1 if two different variables have a negative relationship or a positive correlation relationship. We see that previously stated the surface reflectance bands that are closer together in wavelength are highly correlated. And we also see that there are negative correlations between the water band, the water classification, and the surface reflectance bands, meaning that the lower the surface reflectance bands, maybe the more water it could be. Here we take another look at the distributions. This gives us a nice little line that follows along with the distribution and might be a little easier to look at. We see kind of the same distributions, and we can just kind of see the relationship of water and land between the two. We can also target specifically the distributions of specific features when related to this corresponding label. This first one is the surface reflectance band 1 corresponding to the water label. The water label is the one down low. The land label is the one up top. We see that there's a pretty normal distribution up top with a higher median value. And then down low, we see kind of a different type of distribution for water, where most of those trend towards 0 and much lower than the land distribution. We can do this again for all of the other variables in our data set. We see pretty much similar things. Some bands have closer together distributions than others. And some bands, it's pretty easy to tell the difference between what a land pixel might look like and a water pixel might look like based off of the distribution of the variables. I'm going to keep going. So now that we've taken a look at the distribution of our variables, we can start looking at outlier detection. Finding outliers is important to understand those corner cases where our models might not perform as expected, or where we might need additional training data from. There are several ways of finding outlier values, but we will concentrate on Turkey IQR for this example. Turkey IQR rule says the outliers are values more than 1.5 times the interquartile range from the quartiles, either below Q1 minus 1.5 IQR or above Q3 plus 1.5 IQR. Thus, we can simply calculate outliers per column feature by taking the necessary percentiles. Here's our function to do that. Here we see the floor, which is the Q1 minus 1.5, and the Q3 plus the 1.5 interquartile range. For example, we do this for NDWI2, and we can get the outliers from NDWI2. We see these are really low or really high values. This might tell us that there's something wrong going on in the calculation of NDWI2, or that there's something wrong in the surface reflectance bands that are leading to these calculations being way off from the normal distribution. Next, we're going to look at feature engineering, or creating new features. There are cases where our features might not be enough for our model. We might have a small number of features or a set of features that might not be representative enough. One general approach to solve this is to use feature engineering techniques to increase and or improve our dataset representativeness. For our water classification example, we do not need any feature engineering techniques since we were able to perform accurate detections by simply calculating several indices and using the original optical bands. However, this might be necessary in other problems where your data by itself might not provide enough representativeness. Here we have a function to do polynomial features between the surface reflectance bands, or the features in our data set. These are going to be relationships between the surface reflectance bands, and we can generate a variable for each one of those. Here we simply produce the combinations of the bands, and this increases our feature space from 10 to 65. For an algorithm like a random forest where decisions are being made, this could provide a substantial improvement. Algorithms like convolutional neural networks might not need this since they can extract patterns directly out of the data on their own. Here we see the updated data set where we have the usual features that we've been looking at before, but also we have additional features, which are the combinations of each of the bands. We see that we've upped our column count to 66 from 10. Next, we're going to look at dimensionality reduction using principal component analysis, or PCA. PCA is a technique that transforms a data set of many features into principal components that summarize the variance that underlies the data. This can also be used to extract the principal components from each feature so they can be used in training. Here we apply the PCA algorithm, telling it that we have 66 columns to apply it to. We apply that transform to our data set, which is the data frame. Here we see the output of the PCA algorithm. We have a sample here of 5 rows. We can see that 66 columns are accounted for. In each of them, the output of the PCA is the removing of the variance. In summary, well, what have we done? We've downloaded a MODIS-based data set for training, which we will use in the next portion of this training. We've performed exploratory data analysis on the provided data set and understood some of the characteristics of the given data set. We've introduced several feature engineering techniques for dealing with no data and to increase the training data representativeness. We've also provided additional tools to deal with the data and drive physical conclusions before going into training our machine learning model. Now I'm going to hand it over to Jules to talk about training and testing of the random forest.
Now, to start the training and evaluation of a model, we need to go to the GitHub repository and click on the Google Scholar link on train and evaluation. To start this section, we need to obtain the data set. And these particular cells help us to download all the data that we need for this here. In order to design a Python workflow, it's important, first of all, to import the necessary module that we need for our application. And here we have a list of important modules, and I want to highlight a couple of them, especially the one related to a scikit-learn. In this particular cell, we import all the necessary scikit-learn tool that will need for our application. On top of scikit-learn, we are going also to we need also some kind of visualization tools in Python, especially Seaborn that is needed to have some kind of statistical plot, and also Matplotlib to have basic plot. On top of that, we need also some kind of spatial related tools, especially OSGeos and Folium. Now that we have imported all our module, it's important to consider to set some kind of parameters that will need to download the data, and also to determine what kind of features we need to extract from the data set that we have. And it's important to note here that the feature that we selected here were done based on the exploratory data analysis work that Caleb did previously. The first thing that we need after we selected the features, the first thing that we need to do is to load the data. In machine learning, we need to split the data set into two groups. After we download our data set, we proceed to split into a training set and test set. It's important to see that the water column is set, has the Y features, and is dropped from the X features. And it's important to note that if you look at the shape of the training set and the test set, we have exactly 800 data points in the training set and 200 data points in the test set. It's split like 80% for the training set and 20% for the test set. For this exercise, we have downloaded our data directly from the database where we already had made the split between training set and test set. But in real life, that is not the case. And we may need to use the scikit-learn tool, train test split function, to really split our data. And here is how it can be done. Something that's very important is if you want to duplicate the result, especially when you do the training, and you want to have anytime that you do the training, you want to have exactly the same result, it's good to use the random state and the random state parameters so that the result can be easily duplicated. And also in this particular case, we say that the training set, the size should be 80%. In general, and we want to mention that 80% is not some kind of a set number that can be used over and over, and it's application dependent. Sometimes it can be 70%, 60%, and depending what depend on the application. It's also very important to find a little bit the distribution of the water in our case in the training set and the test set. As we can see here, if you count the number of values, you see that we are almost 50% of the data are water, and on both the training set and the test set. So we can use the stratification parameters to really mimic the distribution of the water in the training data set and the test data set to have some kind of similar distribution in terms of water. So we pass the stratification parameters in the split function, and that allows us to have some kind of even distribution of water in both the training data set and the test data set. Once we have our training set and test set, we can proceed to prepare our training model for training. One technique often used to better validate the robustness of a machine learning model is the k-fold cross-validation method. Cross-validation is a statistical method used to estimate the skill of machine learning models. When using k-fold, the data set is split into k number of subsets. K1 subset then are used to train the model, and the last subset is kept as a validation set to test the model. Assuming that we have a 5-fold cross-validation, we want to use a 5-fold cross-validation method. Basically, the data set are going to split into 5 groups. The first group will be used for testing, and the remaining 4 groups will be used for training. And we are going to rotate the groups until we run the model 5 times, and each time we are going to get the scores. That is the idea behind the k-fold cross-validation method. Here we are going to set the value of k to be 5. Basically, we are going to split the data set into 5 groups. Before we proceed, we need to have some kind of basic statistic on the training data set. And we use the describe function to really produce some kind of the mean, the standard deviation, and the different type of percentile. That gives you some kind of idea of the distribution of each features and see if any identify possibly some kind of outlier. But the work was already done in the exploratory data analysis. We can use thresholding method based on our physical knowledge to extract interesting features of outlier that we may want to visualize later when evaluating the model. And we define this particular function to identify some kind of outlier that will be used later. Model definition and training. In this particular application, we are going to use the random forest method for training the model. And in order to define, and we need to first define some kind of parameters that are needed for the random forest. In this particular cell, we set all the needed parameters that will be needed to define the model. After we define the parameters, now we need to pass those parameters as argument of the random forest function, and that define here our model. The classifier is our model. Now, in order to use the k-fold method, and we remember that we set k equal 5, now we are going to go to a set of iteration where we are going to train based on the 5 groups. We are going to train the model, test the accuracy of the model, and determine some kind of score. And based on the value of the score, we are going to determine if that particular the model is good enough. And don't forget that in terms of score, the ideal score is 1. If the closer we are 1, the better we are. As you can see, when to test the accuracy of our model, we have some kind of accuracy that above 0.95, and we are closer to 1, and that is give us some kind of good indication that perhaps the random forest can be a good model for that for this particular application. As you can see here that we can have an accuracy of about 99%. Now that we have done the k-fold analysis, we can now focus on the random forest model. Now the random forest model will be applied to the entire training set, And when we are done with the training set, we are going to go to the test set. But it's very important when you define some kind of model, the model has to be performed in an acceptable way with the training set first before even moving to the test set. Because if the score is very low in the training set, we don't expect anything good to come out of the test set. So it's perhaps you need to redefine some kind of parameters. In this particular example, we define again our random forest model. We apply it to the training set, and we see how it fits well with the training set. And now we go and we check what is the score that we have on the test set. And we have a score of 98%. That is very good, though we may have something better, but a score as close as one, has this one, give us an indication that more likely we have a good and acceptable model. Now I'm going to pass to Jordan, who's going to continue with the evaluation of the model.
Okay, so now we're going to proceed to do the model testing and training and testing of the data through validation. So once we have actually trained our model, we can then proceed to use this best model that we found from the k-fold cross-validation, and then use that model to perform validation of the actual test data set. First, we're going to get some more of the model metrics. The first thing that we need to do is load the actual best model that we found from the k-fold cross-validation, and then get the score over the test data set. And we can see that we have a score of 99. In many applications, and since this data set is small, this might be, let's say, an excellent score, but in other applications, we could actually be seeing an overfitting effects of having a small data set. So we do need to make sure that you kind of test on a test data set or a validation data set that is hard enough or that has complex dependencies on the test data set, so you can evaluate how generalized your model is or how good your model is to predicting unseen samples. Once we have the score of our test data set, we can then easily perform predictions over all of our training data sets, test data sets, and then create an object for storing those probabilities. And the probabilities of the random forest allow us to understand how good the model or how confident the model was in regards to predicting individual observations. By calculating the probabilities from each one of the features from our data set, we can understand if our model was simply randomly outputting decisions or if it was actually being confident enough to provide probabilities for each observations that are higher than 50%. Anything below 50% in regards to the actual probability means that we'll be kind of in the low range of not being able to assess very well how a pixel is performing or with the actual class of that particular pixel. In this graph over here, we're looking at some of the probabilities, and we can see that we have huge peaks on how confident the model was in regards to water pixel, and then how confident the model was in regards to land pixels. Know that we don't have many occurrences on that middle range between like 40% and 60% of probability, which means that our model leans towards more confidence along both ends of the classification problem. Besides looking at some of the probabilities, we can go ahead and look deeply at the actual scores and getting other metrics besides accuracy. We can look at recall and precisions, looking at how the model is doing in regards to like false positives and false negatives. We can also look at the F1 score, which is basically the harmonic mean of precision and recall. And we can also look at some of the confusion matrix to see where our failures or where our missing features land on. And in this example, we have that we calculated properly 119 features on both ends, but then we misclassified some of the pixels between water and land, basically overcommitting to one of those. We can also look at the receiver operating characteristics of the model, which is going to tell us our rate between true positives and false positives. And the idea here is that we want to have an ROC AU score at least of 1, and know that we're actually matching that pretty well in regards to the actual performance of our model. And again, depending on the model that you might be training on, it might be more complex. You might have an ROC curve that could be a lot smaller or smoother, which would tell you that your model is performing at least decently, or if you're missing any training data or additional feature engineering to improve your model. Once we have trained our model, we have seen that the accuracy score and some of the other metrics that we have been using are pretty substantially positive. We can look at how the model is looking at things. How is the model learning? And the first step that we can do here is to do some permutation importance to look at what features from the data are the most important for this model to perform the proper classifications that it's doing so far. If we look at this graph over here, we can see how the importance of each one of the variables is in regards to how the model is learning. And we can see the surface reflection span 2 is actually one of the most important features at the time of doing the selection between land and water, and also the NDVI, who continues after that one. We can also see that the NDWI1 band is the least useful band to actually talk on the prediction. But at the end of the day, some of these features, they might not be showing a lot of permutation importance on the graph, but when they are combined or when they are removed, this permutation importance can change just because of how our tree structure is looking like on the random forest. The last step is to actually save our model. We have looked at the model, we have looked at how the feature importance deals at the model, but we can now save the model so we can do additional predictions. And we have so far been looking at predicting on a tabular data set, but we can also take rasters and then predict over them by modifying or pre-processing them to account for a tabular data set. So the first step is to download some of our GeoTIFF files that we have uploaded to the database, particularly using the Hugging Face repository for this tutorial. Then we can get a list of those files by only using regex options and by taking all of the files and individual bands and stacking them into a single raster. Once we stack our bands into a single raster, we can then proceed and do some of the feature engineering by calculating the indices or vegetation indices that we have been using before to do the training. In this case, the NDVI, the NDWI1, and then the NDWI2. And we can do this on the fly. So when we get a GeoTIFF file that only has the surface reflectance band, we can calculate some of these indices without needing to look for additional external data. Once we have created our data set and we have an array of features, we can then look at some of the imagery and then we can just start predicting. And know how we came from what a array format we has an input to then a tabular format that we can then use for doing the predictions that we need. The last step here is to actually go through and perform the prediction and know how we are just getting the classifier and then 1, performing a single prediction, and 2, outputting the probabilities per pixel or per actual feature to see how the model is performing for each one of those features. And this is really useful and can be used as a QA mask because you can actually take the uncertainty of those observations from the prediction output. The last piece of here is that we then want to reshape our tabular data set into the exact shape of the GeoTIFF that we initially predicted. So once we reshape our data set, we can see that we have a single band array with all the probability predictions per observation. Once we have our prediction, we can then perform post-processing techniques. And many of these post-processing techniques can include smoothing the imagery that you're predicting on. It could be removing small observations that might not be relevant to the actual product and that might be noise from the model. But in this case, we're only doing post-processing by applying the QA mask that we take from the MODIS dataset. And the idea here is that we read the mask and then we add no data values to all of those features that we know are for sure, or uncertainty features or features that are just not relevant to the final product that we want to generate. Once we have produced our QA GeoTIFF, we can then proceed to visualize it on an interactive visualizer. And in this case, we're using Volume. There are many alternatives out there, but the idea here is that you want to relate the performance of your predictions across the spatial extent of the data. There are cases where you might have representative training of particular observations based on, let's say, the spectral variance of them. But there might be some cases where you might not have enough spatial representativeness on your training data set to account for some of these observations. So in here, what we do is that we create a stack of a base map taken from Google satellite, and then the actual prediction of our water mask. The water mass is in here, and this is the Lake Powell, which is our tile of interest. And you can see that if we turn on and off our water mask, we do predict the Lake Powell observations from this base map. We can also see in other locations where we might actually have some other water bodies that we're identifying, and then even some noise that can be taken on from other locations where there are no water bodies or water pixels attached. Okay. So as a summary, we have downloaded a MODIS-based dataset for training and testing a model. We have performed additional exploratory data analyses on the provided dataset to complement the information we already have for training and testing this model. We have trained and performed inference using a random forest model of a binary classification problem, which in this case is getting water surface extent maps. And we have also created interactive visualization by predicting both tabular and then raster-based data sets across the random forest model. We have also provided a quick overview of model explainability, which we will dive in more details on a future session in regards to how to understand how the model is thinking and then how the model is learning. Last but not least, we provided some cross-validation techniques to understand how the model can be trained automatically in several iterations of the training dataset to get the best model out of the existing training dataset that we might have. So just as a reminder, we have an assignment for this session 2 topic, particularly looking at some of the techniques we already used and then expanding on them. You can just click on the Open Google Colab button here, and it would take you automatically to the assignment notebook that you can work from.
Thank you very much, Jordan. Before we open up to address your questions, let's review what we did here today. We hope that after this part of the series, you're able to see some examples of downloading the training data and doing some exploratory data analysis, extracting training data, taking a look at some metrics and evaluating your model, and then a hands-on Jupyter Notebook experience on a MODIS water classification case study. Looking ahead to part 3, the final part in this series next week, we'll cover an overview of model tuning, a little bit on parameter optimization, an exercise to optimize existing models, and then we'll also go into another exercise doing improvements to the MODIS water classification model. So we hope that you join us for part 3. If you have any questions, you can contact myself or Arset colleagues with the email addresses here. As a reminder, here's the course webpage where you can find all the materials, including the PowerPoint presentations, the videos, links to the Google Colab homework in Jupyter Notebooks, as well as the homework link that will be available by May 4th. This is also our primary Arset website you can check out for other great trainings. Follow us on Twitter for our trainings, as well as exciting announcements from NASA's Earth Sciences. Now let's enter into the question and answer period. Please enter your questions in the questions box, and we will answer them in the order in which they are received. Thank you.
Thank you, Brock. Hi, everyone. My name is Melanie Follett-Cook. I am project scientist for the Arset program, and I will be moderating the Q&A today. So let's start off. Question 0. We saw a couple of these questions in the Q&A, so just want to have some clarification on the homework. So as you complete the assignments that are linked in the Arset GitHub machine learning training. We have a link to that in the chat. You'll see some kind of guiding questions at the end of each. At the end of part 3, so at the end of the completion of each part of this training, we will open up a Google form homework, at which point you can enter in your answers to the questions there, and that will be the homework submission. So there's nothing to submit anywhere until we open the homework at the end of part 3. And you can access recordings, Q&A docs once we've posted them, and the homework from the training webpage, which is linked here. Question 1. Are the MODIS 250 meter data corrected for bow effects? In other words, enlargement and stretching of the pixels because Earth curvature at the edges of the swath. So Gian, you covered this part. Did you want to take this question?
I answered that. This is Mark. I answered that one, Melanie. So, you know, the MODIS. So yes, the MODIS data is affected by the bow tie effect. There's no real correction for that. It is mitigated by gridding the swaths into gridded tiles, as referenced here in the L2G product. So the pixels in the tiled products are identical size, but they are, you know, the underlying observation is still the bow tie affected observation. There's a lot more information you can get by following the link there to understand all of this. I don't think I want to use any more time here to go into that. But what we do in our production algorithm is just exclude pixels that have a very large viewing angle.
Great, thank you, Mark. Question 2. In the homework for part 1, we did the k-means with CPU and GPU, and I'm getting very different results. The number of grid points assigned to each cluster is very different. Is that how it's supposed to be?
Yeah, I can answer that one. So oftentimes there are actually differences between CPU and GPU algorithms. And this is because of some pieces in the parallelization of these. So these differences, they should not be significant, but they can just be present. It can just be like calculation errors inherent from some of the like processors that are being merged at the end. There are some of the difference that you might see in the actual like centroid calculations of the k-means. So don't worry about it. The main idea of the k-means algorithm is just to calculate some centroids from the spectral data we're fitting into the algorithm. So they should at least provide some segregation between the spectral values.
Thank you, Jordan. Question 3. What are some of the key methods used to remove outliers from the data once detected?
Yeah, I can answer that. So there are generally a few methods that I didn't get to all of them, but for removing the outliers, I gave a link, and I can basically there's a few pandas methods that you can use that just gets rid of outliers based off of the number of standard deviations. It's really up to you as the user to determine how you want to remove or which outliers to remove. But if we could copy and paste that link, that'll give a coding example.
Great, and as a reminder, we will post this Q&A, so the document that you see, in just a couple of days after the completion of this part. So everybody will have access to those links. And it looks like Natasha is copying into the chat right now. Question 4. Can bias correction help to improve the quality of data sets? Also, why don't we use -999 to represent missing values rather than using mean values?
So this is Mark again. I'll jump in on this one. So there's some disagreement among us developers on this particular one. It kind of has to do with your point of view about interpolating data or not. I come from the camp of never interpolate under any circumstance ever. Just leave a hole and let it go. There's definitely other camps that have less strong feelings about interpolating output values or input values. The result of the answer is if you interpolate values, then you're going to get some unknown response. So it's really down to the tolerance of the project for having holes in the output data. If you can't tolerate holes, then you need to interpolate. If you can tolerate holes, then in my opinion, you're better off leaving the values that are missing. Just leave them out and let there be a hole. So it's a judgment call.
Thanks, Mark. Did anybody else want to weigh in before we move on to question 5? Sounds good. Oh, Caleb, I'm sorry.
I was just going to say Mark summed it up pretty well. Just to specifically answer why not negative 999. Generally, if you're gonna, so ideally you want to just get rid of it and not fill it in with anything. If you were to impute something, you'd want to take a statistical measure to impute a value that kind of makes sense in the data distribution and not use some sort of placeholder like negative 999.
Thanks. Okay, question 5. Is there any guideline or accepted practice for how high of a correlation coefficient should prompt you to discard one of the variables? There's often high correlation between spectral bands, but they still contain distinct information.
I can jump into that one. So from the data science and statistical point of view, any of the features that would have kind of a correlation higher than like 0.95, you normally just drop them in algorithms that are just, let's say, decision-based. Now, there are other algorithms that you could even just allow them to be there just because they're looking at nonlinear relationships that might not be represented by some of the correlation matrices like the Spearman or the Pearson. It's going to depend on the use case, but some of the best practices are just like dropping some of these highly correlated variables and allowing your machine learning decision model to just extract features out of them. In hyperspectral data sets, then you kind of go into more complex details because you're then looking at some really small deviations between these bands. So you can go into like principal component analyses or other more complex algorithms that can group some of these like individual features. And you can look at the variance from there.
Thank you. Question 6. What is the difference between random tree classifier, or RTC, and random forest classifier? Which machine learning classifier is also good for coarse, moderate, and high resolution satellite images?
I can jump into that one then. So generally speaking, the best classifier for like fine spatial resolution data is going to be one that might not be the best for like coarse resolution or even like moderate resolution. So some of the times we actually leverage spatial algorithms like CNNs or convolutional neural networks to do some of the very high resolution imagery classification just because it can take into account individual pixels, but also surrounding pixels for the neighborhood to actually calculate some of these predictions. So it's going to also depend on, let's say, the resolution of your data, but just take into account the coarse resolution, you might not need some of those spatial knowledge or information to do some of these predictions.
Thanks. Question 7. Can we differentiate minerals using deep learning models on hyperspectral data like Hyperion data?
I'll take that one. So yeah, this is obviously an open area of research. There's definitely been success in looking for certain types of minerals using not only hyperspectral data but other instruments such as Aster. It really depends on exactly what the minerals are, and you have to consider the spatial resolution of the spaceborne instruments in particular, because they tend to be much coarser in terms of being able to identify the feature. The feature has to be large enough for the instrument to have seen it, and then to be able to develop an algorithm to detect it. So it's a complicated relationship between spatial and spectral resolution to be able to detect minerals on the surface.
Thanks, Mark. Question 8. Can you discuss the bin width sensitivity in the histogram? What is the importance of the box plot over the histogram?
I can take that one. So bin width sensitivity, so the choice of bin size for a histogram can certainly affect like the appearance and interpretation of a histogram. If a bin is too large, it could be a little too coarse and fail to capture details of the distribution that you might want to see. Too small of a bin width, and you could get a histogram that's a little too detailed and captures a little too much noise and doesn't fully capture the underlying distribution that we're trying to look at. As far as like box plot over the histogram can show us information such as like the central tendency, the spread, and the skewness of the distribution. A box plot is better to show something like the median and the interquartile range, and any outliers or extreme values. I guess a box plot can provide a quick visual summary just of those things over a histogram would be my first shot at it.
Thanks. Question 9. When you take a sample of the data to conserve computing costs, is this process randomly selecting rows?
I can take that if no one else is. So yes, when in the case we were just randomly selecting a subset just for the simplicity of the demo. In a science scenario, you'd probably use the entire data set if you have enough computational bandwidth. You don't want to lose any data. If you don't have enough computational bandwidth, you could always, stratify a subset that might be fully representative of the training data set to do some EDA. It'll only be really useful to inspect that data, and none of this will really be useful for data cleaning, since you might be missing out on some important rows or pieces of the distribution that you really want the model to capture.
Thanks. Question 10. If we want correlation with the bands and multiple classes, for example, water, forest, settlement, etc., does it work with this heat map correlation chart?
This was me as well. That can certainly work. You can just add those classes as each an individual column, and you can use the same exact method call, the df.corr, and that'll give you a correlation between those classes and those rows and the rest of the features. So that's certainly a one way to do it.
Question 11. Can you tell me a bit about rank of data and plotting of Pearson rate correlation in machine learning?
I can take that one. I was still typing, but so the basic idea is that you can even see correlation using scatter plots. But we use some of these Pearson correlation just to get that statistical value that we can then use to kind of observe or quantify some of these correlations. The ranking of some of these correlation matrices is just basically you have these two variables that you're going to then be ranking per feature, like 1 to the biggest number, 2 to the second biggest one, etc. So at the end, what you're finished doing is just doing a square of the differences, and you just sum some of those to remove some of the like negative values, etc. So it's basically a correlation given two variables that you can then minimize or get the values from the correlation calculation or the statistics to then plot into like a simple confusion matrix.
Thanks. Question 12. What is the maximum size of an image that is practical to work with pandas?
Yeah, there's no real maximum size. It all depends on the limits of the resources that you're working with. Remember, like Pandas only takes tabular formats. That's why we converted a raster into like a per pixel data set. An image that's 4800 by 4800 that's turned into that format of data can fit very comfortably into a Pandas data frame. Eventually, you're going to run out of memory with a large enough image. One method is to use what's a tool called Dask, and they implement something called also a data frame, but it basically uses Pandas and it splits up really, really large data sets into something that can work in memory and kind of works in parallel to perform computations on these data sets. And you know, we can do something with like 1 billion rows in there. It just kind of brings stuff up from disk and works on them and then puts them back. So no real limit, just depends on the resources. And there are tools if you run out of resources that can help you.
I mean, if possible, I may add also to what Caleb just said, that when you use X-array, the calculation are done out of memory. Basically, you are going to bring everything in memory, only what you need. So you can manipulate the data frame as large as you want. It doesn't matter. Even billions of data points, doesn't matter. X-array is going just to read, to bring up to memory what is needed at any given time for the calculation.
Thanks, Jules and Caleb. Question 13. Will we be able to plot the results of the PCA? It looks like the answer is typed out here. It looks like not in this exercise, but you can take the output array from the PCA output, reshape it, and plot it using visualization tools like Matplotlib. Question 14. As far as I understand, Tukey IQR works well for normal distribution, but most of the band values in the dataset are skewed with a long tail. Are there any methods more fitted for data like this?
I can answer that one. So there are many other techniques. We just kind of use or introduce the topic of Tukey IQR because it's one of the like main ones that are kind of used in the data science realm. Regarding like multispectral data, the idea is that this method are going to be more focused on like local and global neighborhoods. So a simple distance calculation like Tukey IQR might not be the best one at the end, but there are other algorithms like isolation forests, local outlier factors, etc. that you could use. We added some references there that you could kind of try or give it a try. And scikit-learn provides even more other outlier detection algorithms that you could try for your data set.
Great. Question 15. While cleaning the data, if there are many null values, what kind of techniques can be applied for filling the data gaps? And I see the advice here is it would be better to exclude those data from the training than to fill them. Did anybody want to add any additional information?
This kind of thing.
Yeah, that's Mark again. applying my own bias. So somebody else can weigh in if they want to.
I was just gonna say this is kind of linked to the one of the first questions that we answered in regards to never interpolating data. And again, this is gonna be based on your use case. If your data set or kind of your use case is not, let's say, reluctant or gonna be affected by interpolating some of this data, you could interpolate using a couple of like mean or even like median values, etc. But again, this is gonna bring noise to your training data set. So it's gonna depend on how much noise you want to bring into your data set, and if your data set is really like extremely small that you might need to use this. If your data set is big enough, just remove them and make your life easier.
Okay, moving on to question 16. How do you decide on the values for the hyperparameters? Do you do hyperparameter optimizations?
We're gonna discuss hyperparameter optimization in session 3. So just be around. We're gonna discuss that.
Stay tuned for next week. Question 17. Do we use a training data set to train the algorithm? Even though we have 80% of the data as test data, why do we classify it to 4 training data sets and only 1 test data set?
Yeah, I think this was maybe in regard to maybe a little bit of confusion with the k-fold method. So we do use the full training data set. What we showed is with the k-fold is we do random splits in the training data sets for like something like 5 times. And we get like a randomly split training data set and a validation data set. And you run through this multiple times. And that's just basically to get a better idea of if the model is generalizing well on data. So it sees the entire training data set without having to fully take out 20%, for test data. We did actually both. We took out 20% and then used the 80% for the k-fold. And that's perfectly valid as well. It all kind of depends on what route you want to go down. So I'm not sure if that fully answers the question, but yeah, we did train the data set train the algorithm on a full data set.
Thanks, Caleb. Question 18. How do we train the model without the masking data? As in unsupervised clustering first, then using them for masking based on those clusterings.
Sure, this is Mark. I'll take that one. If I understand the question correctly, the model is trained to understand the spectral values regardless of their location. That's why we extract to a tabular form so that we can just train the model without respect to the location where that value came from. So when we do that, then you can apply this back to once the model is trained, you can apply it back to imagery data, because from a coding perspective, an image is just an array of numbers. So it doesn't care whether that's a table form or in a geotiff. The code is going to treat it as an array either way.
Okay. Question 19. After getting a set of results, how can we determine whether we need to adjust our hyperparameters versus selecting a different machine learning model?
I answered that one too. So what I would do is perform validation on the output map, which obviously is the model prediction, to determine the actual quality of the map itself. If the map validates to a level that's acceptable to you, the operator, or the principal investigator of the project, then you're all set. But if it doesn't, then you need to either tweak the training and tweak the model, or if it's horrible, then you might consider looking at a different method. So again, it's a bit subjective. The acceptable is determined by the project lead.
Question 20. My Colab session is crashing every time I try to do the Colab assignments, even though I've selected GPU for my runtime. What should I do?
I provided some insights there. Ideally, just try to fully restart your runtime and just kill your session and just try again. Another piece of information is that we have some prompts on the notebook where you need to kind of restart the session so you can load the GPU library. So try to follow those in order to get your GPU's drivers in session properly configured.
Thanks, Jordan. Question 21. Could you talk more about why 50% is used as the prediction accuracy threshold?
I started answering that one, but I can answer it before typing. So the closer the probabilities are to that 50% threshold means that the model is least certain based on class A or class B. And this is now that we're talking about this specific water versus not water example. If the probability is closer to, let's say, a 1 or 100, it means that the model is certain that that particular pixel is going to be water. The probability is closer than to 0, it means that the model is more certain that the actual pixel is land. So know that far left and far right deviation means that you're actually taking the probability of A or B. So if the probability is on the middle or kind of in that middle range, it means that the model is kind of deviating to one class or the other, but it's not it's not certain that it's class A or class B.
Thanks, Jordan. Question 22. Are all types of indices data sets available on the cloud? And I think there's already an answer in here that there are many different types of data available on the cloud. NASA is in the process of moving all of its data on the cloud, which will take a couple of years. You would simply have to search to determine if your specific data that you are interested in is available there. Question 23. What options do you have when the training data set is giving you results, probably prediction you do not expect, especially when testing it?
I can take that one. So I guess the first order of business is just evaluate what the model is taking as input. Like, how is your training data looking like? And if you have any wrong training samples that might be deviating the results from the model. Then just try to look at how the model is performing in like doing some explanational AI analyses that we're going to discuss in session 3. If that is not giving you then something proper, next piece of advice is just to maybe like try a different model and see how different the performance is. If the performance is bad as well on, let's say, a second model, it means that there's something wrong with your training data or the way you're pre-processing your data.
Question 24. What techniques can be adopted to improve machine learning computation time, especially on large, high-resolution data sets?
All right, this is Mark. I answered that one. I mean, the easiest thing is to add more compute and run multiple scenes simultaneously on different systems. You know, that's the horsepower answer. The other possibilities are breaking an image up into smaller pieces and then sending those smaller pieces to multiple CPUs, so that you're parallelizing in that way. So that's my best answer. Is going to be parallelization. That's 2 different ways you can do it.
Okay, we'll take one more question, and that will be it for today. Question 25. If we have a lot of features, 100 for example, is there any technique to select the most important ones in Python for random forest?
Jules answered that one, I think.
Yes, I just put there some kind of general statement. When you train a model and you do some prediction, You are also able to determine the feature importance. It's just some kind of calculation. I don't remember the function. That will tell you exactly what are the main features that contribute the most to your model. And based on that feature importance, you can even simplify a little bit the model, because you are going to have some kind of ideas. What are the variables or the features that can be useful for the model? And the other one, you are going to say that they don't even contribute, they don't even affect the prediction. So you can remove them. And something also that Caleb mentioned today is about exploratory data analysis. When normally you do that also, you can have some kind of basic idea which features can be really critical in the prediction. And you can remove the one that are not critical, because in terms of when you have some kind of heat map, you can just say, look, have some kind of basic idea. So the importance and features can be looked at in the exploratory data analysis. Also, after you train the model, you can determine the feature importance and have some kind of basic information. What are the ones that contribute the most to your model to predict, to have a better prediction?
Thanks, Jules. Well, thank you so much to all of our instructors today and our Arset team behind the scenes. That will be it for part 2 of Fundamentals of Machine Learning for Earth Science. Please join us 1 week from today for part 3. That is on May 4th. As a reminder, the recording of this session will be up within about 48 hours, and we will be posting this Q&A once it's final on the website as well. You can find access to the Arset GitHub. Also on that training page, you can find a link in the chat. And as a reminder, we will open the homework. Even though homework is referenced throughout each of the assignments, we will open that homework at the end of part 3, at which point you will be able to fill in your answers and submit your homework. Thank you to everybody for joining us today, and hopefully we will see you in a week. Have a great day, everyone.